Alright. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We start our lecture today with Kitab Al-Fatihah. Bismillahirrahmanirrahim. Alright, good day everyone. I hope everyone is ready to start our lecture today. So today we'll be talking about the new topic on the electrochemical kinetics of corrosion. As you know that we are in the second last topic of the course, which is materials corrosion. So today we'll be talking about a new subtopic that is focusing on the how the sort of what we call the electrochemical kinetics. In this case, let me show you the screen. Yeah. All right. I'll be seeing it shortly. All right. I think everyone can see the screen now. So, electrochemical kinetics of corrosion. Right. This chapter we'll be talking about the basic concept of interfacial electrochemical polarization, and they are relevant and how this topic is relevant to corrosion. Okay? Electrochemical kinetics. It's about how one particular movement of the electron can affect much on the corrosion. Okay. It also includes a discussion on the theoretical aspect of the electrode kinetics, um, um, which relate to the foundation of the understanding of the electrochemical nature of the corrosion. Other some subtopic will include the mixed potential theory, reversible electrode potential, exchange current density, corrosion potential, and corrosion current and Eiffel slopes. Okay, so we shall move to the next one. Yeah. Okay. So when we talk about the kinetic of corrosion, we cannot run of discussing about the electrochemical polarization. Okay, electrochemical polarization. Right. Um, we know that the corrosion to occur, it has to have um, the combination of anode and cathode of the reaction of anode and cathode, which include the movement or migration of the electron. Okay? Let's say we are taking an example in electrochemical polarization. When a metal is immersed in a solution, we call the metal SM, the metal, in a solution containing its ions, which is becoming the M plus. Several reactions may occur, and the metal atoms lose the electron, which include the process of oxidation reaction to become metallic ions or metallic ions in the solution, may gain electron, which involve the reduction reaction to become a solid metal atom. So in here there will be an equilibrium condition across the metal and the solution interface, which to control the reaction that we are having within the metal and the solution. Right. So when the metal is immersed in the solution or electrolyte, the electron will be transferred across the interface until the electrochemical potential, or we call it as chemical potential, also known as some sort of principle. There is a Gibbs free energy. On both sides of the interface are balanced. So it is highly important to have a balanced equation of the solution and the metal itself. So when the balance of the both sides, it has to be like the solution and the electrode should be balanced until the thermodynamic equilibrium is reached. Okay? So during the reaction, the charge transfer rate at the electrode and the electrolyte, electrode is the metal, and also the electrolyte is the solution in the interface, depending on the electric field that across the interface, like some reaction that happen between the metal and the solution. So, and we know that the transfer or the migration of electron involve the what we call potential gradient should be there. Okay, in order something to move from A to B, it has to be a difference of forces, right? So in here, there should be the potential gradient. Okay, and when things are at equilibrium, the net current should be zero, and the rate of oxidation and reduction reaction equal. Okay, becomes equal. So the potential when the electron is at equilibrium is known as also known as reversible half cell potential or equilibrium potential. Okay. So okay, now you are seeing the equation 3.2 here that I captured from a book. Okay, so there is a potential differences between the situation, right? Oxidation and reduction. And when a net current flows through the electrochemical cells and the reversible half cell potential, EQ. Okay, you see that EQ. Okay, the capital E is the potential, and the EQ is the half cell potential. It's called the electrode polarization, or simply the over potential of the over voltage or over the voltage is the N here that you see. Okay, N is equal to E minus the half cell potential, E equation, which is in the equation 3.2. Okay, so the over voltage depends on the current density. Okay, um, in here we know that the when there is no net current flow, the over voltage is equal to zero. Okay, so in here we can say that the electrochemical processes that are happening here are heterogeneous reaction consisting of consecutive steps. It means that there are some steps that they have to go to make things in balance. Okay, and oversupply or over voltage control will make the kinetic of the charge transfer reaction at the interface of the metal and the solution, which is the immerse, the place that the metal is being immersed, we call it the solution, is actually associated with the slower step. And this can contribute to the rate of the how we can determine what is the next step and etc. Okay. Electrochemical polarization experiment, are performed for us to study the kinetics of the charge transfer reaction. Okay, the aim is for us to study the kinetics of charge transfer reaction of the electron, of the electrode and the electrolyte. So the solution and the metals. Okay. When cathodic current is applied to the electrode, okay, I tried to find a suitable image, but um, uh, I don't have it here. But in the next one, I'll try to provide at least one for you to easy to remember or to imagine. Yeah. Okay. So when the cathodic current is applied to the electrode, the electron that is accumulated in the metal as a result of the slow charge transfer, um, what will happen next? Okay, this will cause the cathodic polarization to happen. We call it the N just now SC, NC. Okay, so NC always negative. Okay, and the transport of the reactants, like what is involved in the reaction, and the form of the electrode to electrolyte interface is happening during any electrochemical process. This is quite common. Okay, at least one charge transfer across the electrode and electrolyte. So and when there is a passage of current, this step can control the concentration of the reactant by the besides or near the electrode. Okay, and the change in composition alters the electrode potential and resulting in the electrode polarization. Okay. If you see, there is a equation 3.3. Okay. What is 3.3? You see N is equal to ND plus NR plus NP and plus NPH. Okay. What is ND? Okay. ND is the diffusion over diffusion over potential. Meanwhile, NR is the reaction over voltage, and E is the electrochemical over potential, and NPH is the phase over potential. I truly apologize. It's very kind of hard for you, but kind of important for us at least to know. Okay, so NE and the NPH, NE and the NPH phase, you can see the statement here, are called the activation polarization. Okay. And the overall over voltage is the sum of the concentration polarization and the activation polarization. So it gives us N equal to N concentration plus NAC. Okay, NAC is the activation polarization. Okay, N concentrate is the sum of the diffusion and the reaction over potential. So those reactions are taking place. The ultimate goal of all the reaction are to have a balance reaction of the let's say the metal itself and within the solution that is exposed to. Looking back at the, if you see 3.5, right? The equation 3.5. At certain condition, current is controlled. Yeah. current is controlled by the rate of electron. Uh, I mean, like by rate of the electron transfer at the electrode. So at the electrode, which is the metal, can be like we know that there is the electron transfer because electron always migrate. Okay, if the electron transfer is described in equation 3.5, okay, you can see 3.5, the rate of the cathodic reaction is first order in concentration of oxidized species at the electrolyte interface. Okay, you can see that oxygen plus electron. So it gives us two different things here, and you have the O and you have the R. Okay, so oxidation and reaction species. Oxidation, O is oxidized, um, R is reduced. The species here you can see that the oxidized species plus electron, and the reversible reaction here producing the reduced species. Okay. Alright, in here it says that the cathodic rate is defined by the Kc. Okay, CO, where Kc is the cathodic reaction rate constant, and CO is the concentration of the oxidized species. Okay, the rate of the oxidation at the anode is first order in the concentration of reduced species at the electrolyte interface, which is the R, and is given by Ka is Cr. Okay, where Ka is the anodic reaction rate, okay, and Cr is the concentration of the reduced species. Okay, and moving on, if you see the reaction of this, we know that as stated here, the heterogeneous rate constant Ka and Kc, they have units meter per second, and the net flux of the oxygen at the electrode surface, which is the conversion rate of oxidized to reduced, is the difference between the cathodic and the anodic reaction. Okay, that is fine. Both cathodic and anodic rates is proportional to the net current, which is the I, passes in the circuit. Okay, it's actually a simple electrochemical cell. You have cathode, you have anode, you have the solution as an electrolyte. Okay, and that's what is important for us to know the migration of this electron along the electrochemical cell. So now we get the net conversion rate is equal to Kc CO minus Ka Cr. Okay. In here, in equations 3.7, the net current is equivalent to the Faraday's constant, and it consists of the KCCO minus KACR. Okay, while the A is the electrode surface area. A is always the area of the electrode, and this is happening when things are at equilibrium. Okay, you may be like getting it is quite you know heavy for you, but I think at this stage we have to know what is happening here, right? As long as the ultimate goal to have the equilibrium of the two reactions, which is oxidation and reduction. Okay. Okay, we move to the next one. Okay, we move to the next one. In most, so we are referring to equation 3.8, yeah? What is stated here? 3.8. In most cases, the reaction rate constant K follows the Arrhenius equation, which that there is Z exponential the delta G, which is the difference of activation energy, divided by room R T, which is R is the universal gas constant and T the absolute temperature. So if this is the case, the activation energy is independent of the temperature, then the plot of the plot of lone K versus 1 over temperature will be a straight line with a slope negative delta G divided by R. So that is in the case of like it is not depending on the temperature. Okay. So but Arrhenius equation always include the temperature in. Okay. All right. We move to the next one. Okay. From transition state theory, the temperature dependence of anodic and cathodic rate constant is given by okay Kc, and there is a Ka and Kc here. Z is exponential of the delta G divided by room temperature RT. Same goes to Ka. The difference is it's either Ka or Kc, right? So under equilibrium condition, the ratio of the concentration of the oxidized and reduced species is given by the Nernst equation. Those are the basic that we have to be exposed to, just in case that next we will be seeing some sort of plots that establish and develop according to the equation. Okay, so next one is, this is the continuity of rate. It's very complicated, but what I would like to highlight here, if you see in the equation 3.12, in fact we have the figure 3.1 here, right? So the electrochemical free energy change or equilibrium and reduction is depicted in figure 3.1. I'll show you after. It's shown in 3.1a, the difference between cathodic and anodic activation. Okay, this is the thing that we are talking about. Okay, so it's shown in figure 3.1. Yeah, you can see the difference between the cathodic and anodic activation free energies for both redox equation. In equation 3.5 earlier that we have seen before is equal to the standard free energy. Okay, is equal. So everything that happened is back to the aim for any particular reaction. It has to achieve the equilibrium. Okay, this is the thing that we should be focusing on. And with that, we stop here, and then we will continue in the next lecture. All right. With that, thank you.